I'm pretty glad to be here, to have the second time opportunity to give this talk. I think, yeah, the first time I missed because I was quite sick at that time, but it's always a pleasure to come back to Vienna. Maybe I say also some words about my relation to Vienna. It started early with Regina Hitzenberger. I don't remember. Oh, when we met the first time, at that time I worked more in aerosol science and moved later on to ice clouds, but it's long ago. I visited Regina and she visited me, and same with Bernadette. I know her already from her time at DLR in Germany, and so the cooperations never really stopped. And yeah, today my talk about ice clouds over the Asian monsoon and their role in the global climate. So I cannot, from the beginning, my main topic is cloud microphysics. I can show you a little bit how it relates to climate, but the question how they we know how they interact, but I cannot give you an answer about the size of the climate effect because it is not known yet. Yeah, I like to mention it's not only my work here. I have many colleagues that contribute to all the things I will show you, and I really hope to meet the challenge not to bore the experts and not to, let's give a too big challenge to younger scientists. I try to somehow balance between that. But now, enough of introductory words, and let me stop with this quite simple diagram on cloud types in the atmosphere, starting with warm clouds at lower altitudes, and then the clouds more and more turned to ice, and also they get thinner and thinner and thinner the higher they are and the colder the temperature is. So here you see a slight latitude versus altitude, and the color code here is water vapor in the atmosphere. Blue is a lot, and here this yellow-greenish is only very little. So this distribution of water vapor with altitude is simply because the colder the air is, the lesser water it can hold. Most of you, I hope, know that. And this is the reason that also the clouds are getting thinner and thinner, because the thickness of the clouds is controlled by the amount of available water vapor. Here is a distribution of the vertical cloud occurrence. Again, here, so this is latitude versus altitude, and the color code here, it's somehow, this is the highest, here this is the highest, and then you already see here in the tropics, at very high altitudes, we have quite a high occurrence of clouds, which consist only of ice. So these two lines here are the important lines separating liquid clouds from mixed phase clouds. So below zero, clouds can be both liquid or ice, but below this mystic temperature of -38 Celsius, liquid water don't exist any longer, and it's pure ice. So this is now, because we concentrate on cirrus, again a vertical distribution. Thank you. A vertical distribution only of cirrus clouds. And you see here again above the tropics the high frequency, below this black line, which is the mean height of the tropopause. So you see the clouds, some clouds are above this this mean tropopause, but above in the stratosphere, clouds does not longer form because it's getting warmer again in the stratosphere and drier, and in dry air, no cloud can form. So this is now a map of cirrus cloud occurrence. Oh. Of occurrence. The frequency of occurrence of clouds. Spatial, yes, yeah. Here, so this is from a certain, this is over a 1 year period, spatial occurrence of frequency, yes. And here, this is also 1 year average occurrence frequencies over the globe. And here you see again that in the tropics, the highest occurrence frequency of cirrus clouds. So how do cirrus feed back to climate? I want to explain this here with this sketch as easy as possible. So here you see, here you see two types of cirrus. This is a thin cirrus and a thick cirrus. And what happens in cirrus clouds is they absorb the outgoing infrared radiation from the Earth's surface. And so this leads to a warming in the clouds, this absorption. But on the other hand, they reflect the incoming sunlight. So if a cloud is thin, a cirrus cloud, then the net effect is in most cases a warming. But if the cirrus cloud is getting thicker, then the part of the incoming solar sunlight, the reflected part, becomes larger and larger. So the thick cirrus, they have a cooling effect. And also the lower, warmer clouds, which are thicker, as I showed in the beginning, so they have a cooling effect. But this type of clouds, thin cirrus clouds, so this is the only one type of cloud that can cool or warm. So all other clouds, they have generally a cooling effect. So this is a diagram, a global mean radiative forcing from IP. This is the International Panel of Climate Change from 2013. And here you see all the forcing agents. So here the forcing is 0 along this line, and to the right in reddish colors. So this is a warming effect. We all know the CO2 effect. And if it goes to the left and is bluish, then it's a cooling effect. And you can see here that, so this is the overall cloud effect is cooling. But the ice processes, they are poorly represented in the global climate models forecasting the weather. And here you can see the error bar here in the clouds is quite large. And this large error bar, which comes mostly from the ice clouds, so this gives, let's say, quite a big uncertainty in the forecast. So this is one reason to better understand ice clouds, is to reduce the uncertainty in the forecast of the climate. Okay. But here we have another agent, which is called stratospheric water vapor, which has not a big, but has also a warming effect. And so in case in the future we a warming climate, we emit more water vapor, then this can strengthen. And especially water in the upper troposphere and in the lower stratosphere is really sensitive to small changes in water vapor. If we add only a very little amount of water, the climate feedback, the warming is quite strong. So this is also a scientific field where lots of research is done, is to look into not only stratosphere, upper tropospheric, lower stratospheric water vapor, and the process is how the water vapor comes into the stratosphere. And this I will try to show you with this next slide. So this sketch shows you the relation between cirrus clouds and pathways of water vapor into the stratosphere. So here, upper troposphere, lower stratosphere, this region, and here you have again the mean tropopause. And in the tropics, here, we saw already this high occurrence of cirrus clouds, and this is because in the tropics there is really strong uplift because of the heating of the surface by the sun. Gives you strong convection, which can reach the upper troposphere. So the cirrus clouds, they can reach altitudes of 17 or 18 kilometers. So with this convective cirrus, together, water vapor and ice particles are injected into this altitude. And what might happen is, or what happens is that water vapor overshoots into the stratosphere and here causes a warming. The cirrus clouds, they might cool or warm, and the water vapor is transported up to higher latitudes, up to northern, really high latitude in the north, where they also can cause a warming. So there is also water vapor transport from the upper troposphere to the stratosphere along the subtropical jet together with cirrus and the polar jet, but the main source of water vapor to the stratosphere is in the tropics due to this strong convection. So this is now a little bit more detailed view to the tropical upper troposphere and lower stratosphere. And here is a region which is called the tropical tropopause layer. And here is a sketch of one of these huge convective towers that reach the TTL between 14 and 18.5 kilometers. So here ice is injected into this region, but also together with the ice, also water vapor. The water vapor that comes to this altitude together with convection, they can form thin in situ cirrus, which are which would maybe not exist in this frequency without the water vapor from below. And and you have all the ice crystals from below in this region. And so it always jumps down again. Yeah. But to make it even a little bit more complicated, it's not that all the ice crystals and water vapor, they will what we call hydrate this region and maybe transported up to the stratosphere. It is also possible here that dehydration takes place. So that means that the water vapor is again removed from the region. So I go in a little bit more detail now. This is the TTL, stratosphere and upper troposphere. And here you see the water and the ice crystals. And now the relative humidity comes into play. So if it's larger 100% or near 100% and you have small ice crystals, they will probably be transported to the lower stratosphere, and here in the stratosphere is very, very dry. They evaporate, and then you have hydration of the lower stratosphere. But if the relative humidity in the environment is below 100% subsaturation, and then the ice crystals, they will evaporate. They will hydrate the TTL region and also may be transported further to the stratosphere. But if you have larger ice crystals together with supersaturation, so relative humidity larger than 100, the ice crystals will grow. And when they grow, they simply fall out. And this is what we call dehydration. I hope that I can explain to you that it's a quite complex system in where cirrus and water and relative humidity, they control the amount of water in the UTLS and control together the transport, the amount of water vapor in the TTL, and the transport to the stratosphere is controlled by ice crystals. So this happens all over the tropics. I think here is my summary of this part of the talk. Yes, the tropical cirrus are the most frequent worldwide, and they can have a warming or a cooling effect to climate, and they also control the amount of water vapor in the upper troposphere and lower stratosphere, where the water vapor causes a warming effect. The Asian monsoon is of special interest because it is the worldwide largest weather system. Here's a satellite image where you can see how huge this Asian monsoon anticyclone, how huge it is. And we observe, let's say, the highest updrafts shooting ice crystals together with water vapor in the upper troposphere. And for that, it's quite interesting to investigate the Asian monsoon. There's lots of research on Asian monsoon and the connected water vapor transport. As you can imagine, it's not easy to do measurements there. And I'm happy today to present you the first in situ measurements in the Asian monsoon. So this is a work also from the Institute of Stratospheric Research in Jülich. And what you see here, these are air mass trajectories. So you can see here the path of air masses in the Asian monsoon anticyclone. And the color code here, this is H. So here you can see the distribution in the horizontal distribution, but here you see the vertical distribution. Here is longitude now. Potential temperature is a measure for altitude. And you see that air masses from the ground are transported up to higher altitudes and up into the tropical tropopause layer here. Here I zoomed out the tropical tropopause layer, and where you can see that really high altitudes, so this is the coldest point in the TTL, and air masses have a chance to go into the stratosphere once they crossed this cold point tropopause. And yeah. No. So they are picked out of wind fields that we call it ERA 5 from the ECMWF, the European Center of Weather Forecast. So they deliver the data. All the weather forecast is based on these data fields that comes from all the balloon measurements and so on and so on. And from this data, these air mass trajectories are derived. Yeah. And if you have such a strong convection, then it needs only a couple of hours to lift the air mass from the ground up to the TTL. So we know already a bit about the water vapor and the cirrus clouds in the Asian monsoon, and this is from satellite observations. Water vapor and cirrus at the altitude of 100 hectopascal pressure, which is also used as altitude measure. And you can see here nicely that over the Asian monsoon, you have again a high cloud fraction, so a high frequency of occurrence of cirrus clouds, together with here the higher or enhanced water vapor. And I have listed here again the impacts on climate of cirrus, cooling or warming, and there is a direct impact of water vapor in the tropics, and also the water vapor can be transferred up to northern latitudes. But this is a satellite, and so our part now is the in situ observations. That means observations from aircraft, and to somehow, let's say, to somehow validate the satellite observations. So we have not only measurements in the Asian monsoon, so this is the campaign 2017 out of Kathmandu in Nepal. So we have many other field campaigns which we collected all together for 24, and with 185 flights, that means around 200 hours in cirrus up to 2017. We sampled a bit more up to now. And you see we used quite a lot of different aircraft, and also we have some data from our colleagues from the US. So these two aircraft and the data from these aircraft are provided by US colleagues, so to have simply a broader picture. Yeah, this is, I'd like to introduce here, this is the campaign which is called Stratoclim in the Asian monsoon. So with a normal aircraft, passenger aircraft, you cannot reach this high altitude. So if you want to have in situ observations in higher altitudes, then you need special aircraft. And what we used is a Russian aircraft, the Geophysica, which was in former times a spy aircraft. And yeah, we thought that the times of quarrels with Russia are over. Yeah, this is another topic. The people, the researchers in the US, they do the same. They use the old spy aircrafts for atmospheric measurements in altitudes up to 19 or 20 kilometers. This is quite challenging. So you see here, it's only one pilot sitting in the aircraft, and all the instruments, they need to operate standalone without any operator at really cold temperature, because the temperatures go down to -90 Celsius. So it's really a challenge to have good measurements there. So my group, so we had an instrument which is called FISH, and with FISH we measured the total water. This is built at our institute, but we also have under the wing a cloud spectrometer, and this is now what brought me here, because it's the same instrument that Bernadette and Max also operate on aircraft. So here is the whole climatology of ice water content of cirrus clouds that we sampled. So you see here thick cirrus at lower altitudes, and the higher the altitude is, the thinner are the cirrus clouds. So here is the TTL, and here the cold point, and here you see the measurements in the Asian monsoon, and you already can see here in comparison to all the other measurements, the colors are more for thick cirrus. There are thicker cirrus than in the surroundings. And here in this figure, so this is temperature versus ice water content. And the color code here is again frequency of occurrence. Here this is from 125 hours of measurements in cirrus, but without the Asian monsoon. And you see here to guide the eye, so this is a median ice water content, where you can see that the colder it is, the thinner are the cirrus clouds. And here are the measurements now from the Stratoclim campaign, and you can see here in comparison that we catched really thick cirrus at cold temperatures. And yeah, the ice particle sizes there were up to 800 micrometers, which is really large if you catch them at 18 kilometers. On the other hand, we observed also very, very thin in situ cirrus in the TTL, which cause a warming. So the message here is that above the Asian monsoon, we really found the extreme enhanced conditions for cirrus clouds, but also for thick cirrus cloud, but also the thin in situ cirrus. And here, so this is to give you a quick, let's say, or a brief look into the climate effect. Is so these are exemplary cirrus radiative forcing simulations. So this is the optical depth of which corresponds to the physical thickness, and here you see the forcing, and the green here above zero. So this is the warming caused by thin cirrus. I have a slight warming, but a thick cirrus, like what we found in above the Asian monsoon, they can have quite a strong cooling effect. So maybe you can imagine from this simple view that it is, to really implement in global climate models the cirrus clouds, then you need to know the partitioning between the thin and thick cirrus because they are so different. And so this is, for example, something which is not known at the moment, the partitioning, not only for Asian monsoon, but over the globe. So this is my just started last project of my career, is that we will try to get a view on the partitioning between the cirrus types. Okay, now to the water vapor amount in the TTL. It's here now temperature versus relative humidity with respect to ice. And again, the frequency distribution. And out of all these lines, please look only to these 3 lines here. Yeah, this is 100%. So that means here it's supersaturated, this is subsaturated. And these lines means lines of constant absolute water vapor amount. It's here at the cold temperatures, it's 1.335 ppm of water. And so that means the relative humidity here, this branch, so this corresponds to absolute water vapor between 1.5 and 3. So this is now without the Asian monsoon. This is tropics, but without Asian monsoon. And here you see the enhanced amount of water vapor that we measured in the Asian monsoon. This is, it sounds not much, 3 or 5 ppm, but for this altitude region, this is quite a lot. And if you add half of a ppm, you really can see a warming effect. Yeah, this is my last slide, I think. Maybe I'm good in time. Let me guide you through. So I talked about hydration and dehydration, and I explained that dehydration, so that means the TTL is getting drier. That happens when the relative humidity is above 100. So it's this region of the diagram. This is again potential temperature, which means altitude, and these lines here enclose the TTL. So these are ice water contents of cirrus clouds in the TTL in supersaturation. So again, blue is thick clouds, and the color code here is thick, and these are the thin clouds as before. So that means this part of the cirrus, they will not end in hydrating the TTL or transported into the stratosphere. Only the part in subsaturation where or saturation, they might end up in the stratosphere and warm already here. They lead to hydration. So mainly this part of the measurements, which you can see, it happens not too often, that the conditions are in a way for transport, but still the transport happens. And it's not only in the Asian monsoon, because here these are our measurements in the tropics, but without the Asian monsoon. Here you see a patch of higher ice water contents, and this was deep convection above Australia. It's a well-known convective systems which appears at the same place every year, and but it's small scale. And it was dedicated flights into the small scale. So here's the same diagram for the measurements in the Asian monsoon, and you see that the colors for the thick cirrus, they are elevated in comparison to the other tropics. And also here, this is the cold point. We see elevated levels of ice water content. We see the same also for the gas phase water vapor, these elevated values in the Asian monsoon. So there is more water that might be transported into the stratosphere. So in the end, once you see that the relative humidity is, the higher you get, the lower is the relative humidity, and this is because the ice particles, they start to they evaporate more and more, and we don't know their fate. If they really are transported in the stratosphere, we cannot see that from our measurements. So, yeah, this is my main message. I hope I explained you a little bit the role of the Asian monsoon or ice clouds in the Asian monsoon, in the global climate. And I think the new thing that I can present is the first in situ measurements and quantification of cirrus clouds properties, thin but also very, very thick cirrus, and that we found cases of hydration of the TTL and maybe transport into the stratosphere. And I hope you enjoyed a bit and the talk, and thank you for your attention.